Okay, if you don't have any doubts, then we will start. So last session we actually discussed about one particular example is from the Professor Des group. They actually took they took a catalyst with a iron chlorine system which has a uh, iron 2 system, and the iron 3 system takes one electron to generate the one electron reduced species. This is the iron 2, and then followed by further electron transfer and then CO2 binding followed by proton binding and generation of the iron 3 COOH, which is actually uh, this I'm talking about. Okay, I'm talking about this compound. This is actually becomes Mossbauer active, and then followed by further electron transfer is generated the iron 2 and COOH bound species, which release the uh, formic acid by capture of the protons, and then it's generated the iron 2. And the small spectra of the intermediates, it's showing placed here. We have a intermediate one, that is iron 3, as it's reflected that delta EQ is the iron 3 because of the its D6 system, and it's bound with the no, not delta value is the far more negative than the iron 2. Here it is the iron 2 because of the delta delta value is around uh, at more positive direction than this one. So and this is the iron 3 which bounds with the carbon dioxide, and it has some residual iron 2 over here, which is been given by this iron 2, which is dotted one. This dotted line over here, this is the residual. And then here also they took the iron 3, and then further one electron reduced species with the CO2 bounds, and it becomes a COOH, and then they found this spectra. This is the actual data dot, this black dotted line, and followed by this is the fitting data, red dot, and then they actually did some what is that plot simulation, and then they found some iron 2 COH bound system, and then followed by uh, there's some residual Av2 system has been present in that system. So, and then right now we actually go for some other system. Let's start with some system. As we know, some problem, can we solve it very quickly? We can solve some one question. This is that in general question where you can find in your different what is different exams like NET, GATE, or any competitive exam for this most perspective actually included. Let's suppose our I'll talk with the one question is that we have a one question is, this is made by me. You can solve easily by this way. Okay, so we have a uh, nuclei. We have a nucleus. Sorry, nucleus having uh, I value equals to 5 by 2 and it excited to I equals to 7 by 2, and then by capturing gamma ray. Now question is, if there is non-zero EFG value, EFG equals to, now EFG equals to not equals to 0, in that case how many Mossbauer line will find in Mossbauer spectra, in the spectrum. Okay, this is the question. We have a I equals to 5 by 2 and I equals to 3 by I equals to 5 by 2 and I equals to 7 by 2. It's excited to 7 by 2. So, and we have a EFG value, that means electrical gradient will be, electrical field gradient is not equals to 0. That means there is a electrical field gradient will be there. There is a, let's suppose, one nuclei with coordinated with a different ligand, then it's not a symmetric ligand present over there, then there will be an electric field gradient. So if electric field gradient is there, then how many Mossbauer line will find over here? This kind of question you will find in a different exam. This is a very easy question and you can solve it by just thinking how we can solve it. Okay, so let's try to answer this question. This is answer. We have a energy over here, a ground state, excited state, ground state. Here I equals to my 3 by, no, 5 by 2, I equals to 7 by 2. Okay, and the excitation happens from here, sorry, here to here, capturing the gamma ray. Okay, now our here problem is that our EFG is not equals to 0. As we previously discussed that EFG not equals to 0 when my I equals to half or 0. As it is I equals to 5 by 2, if there always be EFG equals to non-zero, it will be splitted into two different line. No, it's three different line. So my this line shall is splitted into three different line. 1, 2, 3. One will be my plus minus 5 by 2, plus minus 3 by 2, and plus minus half. Here also similarly, we have a line over here that can also split into 5 line. 1, 2, 3, 4, 5. Okay, so plus minus 7 by 2, plus minus 5 by 2, plus minus 3 by 2. Oh, 4 lines, sorry. and plus minus half. Okay. So what are the possible uh, transition happens over here? We have a transition around plus minus half true. Sorry. Plus minus half from here to here. Now 3 by 2 to 3 by 2, 5 by 2 to 5 by 2. From starting from the here, plus minus half to we can shortly write it down. Here plus minus half plus minus 3 by 2 plus minus 5 by 2 plus minus 7 by 2. Here plus minus 3 by 2. Similarly 5 by 2 will be this one. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 expected spectra. Should be 12 different lines should be there. But we'll get some lesser than the 12. We have to calculate right now. So the energy gap between now, our main fundamental thing is that energy gap between here plus half to plus minus half to this plus minus half plus minus 3 by 2 to this plus minus 3 by 2 plus minus 5 by 2 to this plus minus 5 by 2 will be similar. Okay, will be similar. And then we'll get one line for these three transition. That means 1, this will be 1 and this will be 1. So we have a one line over here. Now change the color. Take another color. Let's suppose green. Now half to 3 by 2. Half to this 3 by 2. Again here this 3 by 2 to this 5 by 2 and this 5 by 2 to this 7 by 2. Those are the similar amount of energy. That means 5 by 2 to this will be 2. This 3 by 2 to 5 by 2. This one will be 2. And this one will be my 2. No. Previous one. This one. 2. So we have this value. This is the 2 line. Now another is that we have this half to 5 by 2. The energy gap between this plus minus half to this 5 by 2 and the plus minus 3 by 2 to 7 by 2 are the similar. So we have this 3 This one will be the 3. Okay, so we have rest of the thing are the different. This one will be another one. This one will be 1. This 3 by 2, 2 half. This 5 by 2, 2, 3 by 2. This one also similar energy. Okay, so rest of the thing are the different. So we have it 1, 2, 3, 4, 5, 6, 7. We'll have 7 line. In the Mossbauer, we'll get 7 line. Okay, so 1, 2, 3. This one will be my 4. This one 5, 6, and this is the 7. Okay, and we have a something we am doing wrong, I think. This 3 by 2, 1, 3 by 2, 2, half. This one. This energy is similar to the 5 by 2 to 3 by 2. Oh, ho, ho, ho. I did another mistake over here. This 3 by 2 to half is 5 equals to this one will be the 5. This one will be the 5. So we'll have only 6 line. And ratio will be the different. Okay, so what will be the ratio? First of all, 1 is a 3. We'll have another 2 to 2. 3 is to 3. Then we'll have number 3 transition. How many? 2. We'll have 2. 4 will be the 1. 1 is to 2 is to 1. This will be the ratio of the transition. So all 6 lines will be appeared in the Mossbauer spectra if EFG not equals to 0. You can make this kind of problem by yourself and just try to match with their energy gap and energy, how much energy we need. From it you can calculate how many lines you will get from that. If EFG not equals to 0 for that particular nuclei, if nuclei I value is nucleus spin value that is 5 by 2 or 7 by 2 depending on whatever your transition are looking for. If it is I equals to 3 by 2 to transition 3 by 2 to 5 by 2, then you will have it. Similarly you can calculate by yourself. Okay, so that's how you can actually calculate the how much energy you will how much spectra you will get from that. Okay, so this is the problem you can find in your exam. You have to solve by yourself, as just fundamentally you have to think how many transition is possible and how many transition are similar in energy. If similar in energy, you will get this line in that particular only your degenerate state will get, and it will appear in a one line, and the intensity will be different if their transition is one transition is over here, or depending on the how many transition is similar in energy. Okay, so this one problem. Now move to some other problems. I have a note about that, so I'll go through with that. Okay. So one interesting problem is, as we know, problem, another problem, question. So I have a ferridoxine, which is Fe3 ferridoxine, 1 ferridoxine. It is named as 2Fe ferridoxine. That should be named as a 3Fe 4S ferridoxine. So with that, we are providing one electron and record the Mossbauer spectra. What will be the with the spectra line, spectra, number of spectra? What will be the number of line and the intensity? Okay, this is the question. So now I have to answer this question with respect to just simply calculation. We don't need to think about too much. We have to, first of all, we have to know the structure of the iron 3 iron 3 Fe 3Fe 4S ferridoxine. This is a structure which is, this is cubic kind of structure. That's our one corner will be missing. So we have here is Fe, and this will be Fe. S, 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 this, and this will be S16. Okay, this corner is the missing. So what are the possible oxidation change in a one electron transfer? So first of all, this is iron 3, 3 iron 3. Okay, now one electron transfer happens. It generally takes one electron. Ferridoxine are not taking multiple electron in a certain point. It takes each and one electron each time. So but this electron transfer is very fast, so it can produce Fe3, Fe3 and Fe2. Now this is iron 3. We'll expect the iron 3 means your electron, how will be my electron distribution? and this is tetrahedral kind of structure. Then we'll have T2G and EG level over here. 1, 2, 3, 4, 5. 5. We have a lattice is very less. Okay. There is no there is no valence contribution. Contribution. There is lattice contribution. Sorry, this will be 116 only, not the 260. I'm sorry about that. Okay. And this is the ISS. Lattice contribution will be there because of 4 different atoms or one sulfur binds with the cysteine. So there will be a lattice contribution. So we'll have all the iron are in 3. So we'll have 2 line like this. Oops. Transmittance percentage. You have a velocity over here, millimeter per second, and we'll get the line. Okay. Only one line or 2 line will get because of the lattice contribution. We have a EFG not equals to 0. That means we'll have the 2 lines. So, and there is no valence contribution because of that. It's a high spin system, and a 4 coordinated high spin system. All the d orbitals T2G3 and EG3, T2 323, so not T2G, no, it is T2 and E2. So the electron distribution is similar, symmetric. That means it's a symmetric system. So valence contribution should be 0. And as it is that for different ligand over here, it is has a lattice contribution, and for that we have the EFG not equals to 0, and we'll get the 2 lines. But all the iron are in iron 3. All are in similar environment. All are in similar ligand coordinates. All are in a similar valency. So that all are will have the same. What is that? Same energy, everything. So we'll get the only one particular species will get. That means all the iron 3 will get the 2 lines because of the lattice contribution. The spreading will be there. And on other hand, taking one electron, one iron, we expect that one iron becomes the iron 2, and rest of the 2 are remains same. So we expecting that for the iron 2 we will have transmittance percentage, we have velocity over here, millimeter per second, and this is the iron 2. That means we have some lattice contribution as well as some valence contribution because of iron 6, and we'll have T2 3 EG 3. So we'll have energy 1 electron each holes, T2 3 EG 1 electron filled up over here, 1 orbital, and E3. So there is a Valence contribution. Okay, so if there is valence contribution and also has a lattice contribution, that's also, so there will be delta eq value. Delta eq value will be large. Will have a large delta eq value than iron 3. So we'll have, this is the spectra for the iron 2, and it will be middle of this will be my delta value. This is the delta value, and this will be my delta eq value. Sorry, this will be delta eq value. On other hand, the iron 2, iron 3, 3 2 iron 3, that will come into this. Okay, this will be my delta eq value. Delta eq, and this will be the delta value. Sorry to my writing. This is the delta value. This point. This is Fe3, and this will be Fe2. This delta value for Fe2. Okay, so that's the Fe3 is much have a less electron density. It will come at the negative direction to than the Fe2 plus. So as we previously discussed. Now, delta eq value of the iron 3 will be less because of there is a valence contribution. There is no valence contribution in the Fe3, and but there is some lattice contribution. So we'll get the splitting, but delta eq value will be less. On other hand, for the iron 2, we'll have the delta eq value will be large because of the there will be valence contribution as well as the lattice contribution. So delta eq will be large, and that's why the splitting will be larger, and the delta value will be that more positive direction because of the high electron density. It will come into more positive direction. So this and the, so what will be the ratio? As we know, the iron 2 are the one species and iron 3 is the two species. So there will be ratio will be ratio should be ratio will be my 2 is to 1. 2 for the iron 3. This will be the iron 3. Sorry, I can write this way. Fe3 plus is to Fe2 plus, ratio should be this one. The intensity ratio for the Mossbauer line. But in generally, what we get? We get something different. We generally get the actual spectra looks like sorry, I can draw it properly. Okay, so here the ratio we are finding Fe3 to Fe2 or something will be Watch 1:2, but it's supposed to be reverse one, like look like this. But we get this line. Why it is so? Now, if you close look into the structure, it is connected with the sulfur. All the iron connected with a sulfur bridging sulfur bond. Okay, if one iron takes one electron, it actually mixed valence. It generates a mixed valence. There is a antiferrotic coupling happening over there, and one of the iron 3 becomes the iron 3. Rest of the two irons becomes the iron 2.5, and we'll get a average value. So is this actually iron 2? Because no, this is actually in the Mossbauer it is showing iron 3 is there. Okay, you can write it as a iron 3 is there, and this one becomes the iron 2.5, and that will showing 1:2 ratio. This is the one example of the antiferrotic coupling. Okay, so this is the delta EQ value for the day. This is the EQ value for the iron 3, and this is the EQ value. What will this will be the middle one? This one will be delta value for the Fe 2.5 plus, and this one is the for delta Fe 3 plus. Okay, and delta EQ value is the higher for the this 2.5 because of the there will be asymmetric situation over here. Okay, so this is this how people actually ask you to how to solve this problem. So what are the phenomena people are say giving this spectra, and ask you if one electron transfer happens, so why this phenomena is present over here? You have to answer properly. This is how antiferromagnetic. This is because of the antiferromagnetic coupling. Two one iron two with one electron taken to the by my ferrodioxine. It generates a mixed valence iron 2.5 system, and that is the present over here. Two iron becomes the iron 2.5 positive charge, and one iron becomes iron 3 plus, and that is the ratio of 2:1, and we'll get this line because of the iron 2.5 giving me the higher splitting of that the delta EQ value will be high, and delta value will be more positive direction than the iron 3. Okay, this is how you can solve the problem. Okay, so one another problem is we know that question will have Fe3 CO whole 12. So what is the preferable structure? Okay, this is the question. Now if we close look into the Mossbauer spectroscopy, what will be, what are the before going to the Mossbauer spectroscopy, what are the possible structure we can get it from the this molecular formula? We have a very different structure we can get, but right now we can draw some of them, and then we'll let the finalize the what is the structure from the Mossbauer spectroscopy. We'll have the three iron over here, Fe, 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 The metal ion will be dotted line here. The 3 CO, 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 4 CO, sorry. CO, 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 and CO. This is the one structure, and the structure, or the CO can be bridged, make a bridging bond. Here the CO, oh sorry, this will be iron. Fe, Fe. Okay, we have a bridging over here. Here, similarly over here also. Same here also. Okay, the rest of the CO remains over here same. Okay, so this structure is also possible. This is the terminal CO, all terminals. So in Mossbauer spectra, all iron looks like similar. So Mossbauer line, Mossbauer line will be 1. Here also, all the iron, oh, this will be CO, sorry. And all the iron are looks like a similar. So here also, 2 each Fe, 4 bridge ratio to terminal CO. Each iron contains 2 bridge CO, 4 in terminal bridge CO and 2 terminal CO. Okay, and then here also we will get Mossbauer line. Line will be 1 because of all the iron looks like similar, and it will give you the 1 Mossbauer spectra. Now another possible structure. Going to the another possible structure. This is the iron. This is iron. This is the iron. Let's suppose this iron contains. Sorry, we can draw it for another way. Here, 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 here. Okay. CO, 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 CO. Okay. And then we'll have this iron and these 2 iron bridged with to CO. Okay, this is the another possible structure. Here, in this case, we'll get 2 Fe, 4 bridge CO, 2 bridge CO, 2 bridge CO and 3 terminal CO, and 1 Fe contains 4 terminal CO. Okay, so there is a two different distinct iron center is present, and three of them, two are the similar, it having 3 terminal CO and the 2 bridge CO, and another iron have the 4 terminal CO only. So what will be the my Mossbauer line then? Then there is a two different iron over here. So if two the iron over here, we'll get Mossbauer line, two Mossbauer line. And ratio will be 2:1. Okay. Now, question is, which one will give you which one? Okay. Okay. So, see, this iron 4CO coordinate with similar, let's say iron 2 is there, iron 2, and the 4CO is here. It doesn't has any lattice contribution, but this one will have lattice contribution, 3CO one side, another side will be the 2 bridge CO. There will be a lattice contribution. So delta EQ value for this iron, this I can write it iron A and iron B. This is the iron B we are talking about. This is the iron A. For the iron A, next page, here also we can write iron A. It will have a less delta EQ value. Why? Because of lattice contribution is zero lattice contribution. Contribution is well less. Okay. On the other hand, we have a bridge C over here, iron 2, Fe, Fe2, Feb, high delta AQ value. There is a lattice contribution over here. Okay, so the spectra will be looks like the spectra will be sorry. We have percentage of transmittance and we have velocity millimeter per second. The spectra is looks like here. Okay. Understand? This is because of the terminal CO. This is terminal CO bound iron. this line, these two line here, and this line because of the bridged carbonyl bound iron. Okay, this kind of problem we can solve easily by the Mossbauer spectrum. This is the positive sign of the Mossbauer spectrum. Okay, so now we can move some real research problem. That means all are real research problem. Now another kind of research problem is that, okay, this is a problem. Professor Pine and his group from the cultivation science. Professor T.K. Pine. Professor T.K. Pine from the cultivation science ISS. So they try to make a such complex iron 4 complex with a astronautal coordinate system. They try to make this complex, and this oxo species want to transfer it into a olefin group, that is alkene over here, this alkene, to make this peroxo system. Okay, in which it has been done by this hydrogen peroxide. Okay, they want to find this system. Okay, now they generates this iron 4 oxo species, and which is binds with the scandium 1, scandium triplet. Okay, this species has been isolated. This oxo species has been isolated by the Mossbauer spectroscopy, where which is found that delta EQ value is 1. Delta EQ value for this iron 4 oxo species is the 3.15. Why that much high value? Because of the is a asymmetric system. Has a lattice parameter. It will have the electronic contribution because of the iron 4 system. If iron 4 is there, then it will have D4 system, and if it is D4, there will be a asymmetric electronic distribution. That means we will have valence contribution, and also it is not symmetric, so it will have a lattice contribution. Okay, now they also tried with an different reactive species to make a different reactive species, and then they actually able to make this highly reactive iron oxide species. Okay, so to isolate this kind of species, they took a help of the Mossbauer spectrum. Okay, now we have, this is 1.22, 1.17. Okay, this is scandium coordinated. One is the we can isolate. This is the my species A, and this is the another species B. Okay, now this spectra corresponds to my species A. and this is corresponds to species B. Okay, so why it is so? Here the this iron oxide species, where it is, this is the species. She is actually coordinated with the scandium. We have iron over here, and then it's coordinated with here. This is the positively charged species as radial coordinated, and then we have the scandium over here. Scandium triplet. This is actually act as a Lewis acid, and then it will have interaction between scandium, and that will reflects on the delta value because of the its some electron density distributed in presence of the scandium. So it has a less electron density because of the scandium. It actually acts as a Lewis acid, and delta EQ value looks like similar, but it has a lower value than the and delta value of the only iron isonitrate complex, triplet complex. So these two phenomena has been monitored, that this this iron without scandium, and this is with scandium. With scandium delta value is the 1.17, and this has 1.12. So it is more positive direction, iron 2. This is less positive direction because of the Lewis acid interaction of the scandium molecules, scandium complex, and then that reflects on the Mossbauer spectroscopy where the delta value shifts more negative direction because of the Lewis acidity of the scandium. Okay, this is the one example. Another example over here. This is the interesting, very interesting things. Okay, so same group doing this kind of iron 4 oxo species, and taking this iron oxo species, they are actually making a peroxo oxo species, and that oxo species actually transfer into the olefinic group and make a oxo oxidized olefins. Okay, so that will be a organic transformation happening by the help of this molecular iron based catalyst. Okay, so this is the iron with a ligand of pyridine and tri- triazole system. Triazole, this is the amine over here, which is coordinated with ethyl coordinated. This is the ethylene diamine, ethylene diamine, and then this amine is coordinated with a one pyridine molecule over here. This also a one pyridine molecule over here. This is four coordinated system which binds with the iron complex with this other solvated ion, and then if you selectively produce this iron 2, it transfer its this oxo species to the this to this olefinic group and make this peroxo species. Okay, and then that will give the this becomes the highly reactive species, and it's formed a chemoselective and regioselective oxidation of the olefins. Okay, this is the one of the best result has been found by their group, and then they want to isolate this iron 4 oxo species and try to establish the mechanism. Okay, in the mechanism, they are saying this iron 2 generally takes the I, iron 2 to generate this iron 4 oxo species by this oxidizing agent. This is Ibex ester. It can oxidize this iron 2 system to iron 4 oxo, and then this 4 oxo actually murdered by the Mossbauer spectroscopy. In the Mossbauer spectra, it is showing the population of the this iron oxo and iron 4 oxo and the iron 2 oxo will have iron 2 oxo is the iron 2 is 43% and the iron 4 is the 53%, and the delta value, the following delta value has been found for the green one is this green line. This is the iron 4 oxo species, and then it is has a delta value is a less negative because of the iron 4, and the rest of the thing is the remaining the initial one, which is 1. Okay, now in place of the base they found another oxo species. This is the one species which is over here. This is N is protonated, and when N is deprotonated, they will got another species which is over here. This is delta value has been found is 0.05 millimeter per second, and the delta EQ value is around similar to the previous 1A over here. This is 1B, but its population is the 72%, and it has a very highly selectively transferred oxo to the myolipine, and it is actually uh, very reactive species and has been found in the by directed by the Mossbauer spectra. So it is a very big tool. How much this oxo species is present, we can detect by the Mossbauer spectra by deconvoluting the actual spectra. Okay, so it is associated with the my initial this one minus h. This is around 28% over here, and delta value is saying it is in iron 2, and if iron delta value is iron 4 is negative as expected because of higher oxidation state, it will give you the delta value at the more negative side, as the my delta r by r value is the negative. If less electron density on the d orbital, so there is a higher s electron contribution at the nucleus because of the less penetration power of the d orbital. And then the the psi square of sample minus psi square of source will be the high value, and then we'll have high negative value. That means my delta value will be the more negative side. So that's why this is a negative, this is less than 0. So if the higher contribution of the less electron density at the d orbital, s contribution, so s orbital contribution at the nucleus will be high, and the size 0 square value will be high, and then we'll get the delta value will be more negative. Okay, this is the phenomena we'll get from the Mossbauer, and then we find this iron 4 oxo species has been detected by the Mossbauer spectra, and delta AQ value are suggesting the splitting of the this iron 4 oxide species is here. Okay, so that is the problem. We found some literature, and if you found some different example, you will feel free to ask me anywhere. Okay, so we'll try to solve that one also. Okay, now we'll have some other problem. Problem is, oops, sorry. Okay, we'll have one problem is Prussian blue and tarnish blue. What is the difference? In the Prussian blue, we'll have in Prussian blue we have hexacyano. We have Fe two 3 over here, adding Fe3 plus in hexacyanoferrous 2, iron 2, hexacyanoferrous. So FeCN whole 6 2 plus. Okay, so this is Prussian blue PV, and we have a tarnish blue. We have Fe2 plus, which is added to the Fe3 cyanide hexes. Oh, 3 plus. This is tarnish blue. Okay, so but in that case, we are saying that they are forming similar kind of complex. If you add this one, this will actually generates a electron transfer, outer coordination electron transfer happens, which is forming the it will form. So Fe C N C Fe, this kind of complex every direction. Here also same. Okay, so that becomes, it will be 2 and it will be 3. Similarly, here also the one initially it forming iron, here will be iron 2 and C Fe iron 3. Okay, and all other rest of the thing will be remain same. Okay, okay, now this one actually electron transfer happens to one electron transfer from this iron 2 to iron 3, and it will give you the this one electron transfer happens, give you the same complex, and this phenomena has been recorded by the Mossbauer spectrum. How they took both here Also, they took both the similar spectra. That is, we have the iron 2 with the iron 3. Four lines will appear. Here also, they are getting same. This outer line is because of the Fe2. This is focus for the Fe3. They got the same structure. And then why is this happening? Because of this electron transfer happens, they form the same complex. This kind of phenomena they has been monitored by the Mossbauer spectra, where they found what they found with the taking of the 57 enrich 57 enrich, the 57, this is become the 100%. This is 100%. Okay, and they found that they are getting Mossbauer spectra is this one only, because of this is the 1%, around 1%, and this is the 100%. So 1% doesn't appears into the spectrum for this one. Okay, reaction A. This is a line, and this is a velocity millimeter per second. Now they take this iron as a 57 enriched iron, and they found in the B, they found this is the same as initial one. How? This two line for the iron 3 only, but they took the iron 257. This will be 2 iron 2. They show the iron 2 as a 100% line. Splitting will be higher, but they not get this one. This is transmittance, and this is the velocity. Okay, so as the starting with the iron 3 57 100%, we get the 1 2 spectra. Similar spectra has been found when we start with the iron 2 addition to the iron 3 hexacyanoferrite. Then we are getting the same Mossbauer line. So why this is happening? So because of the electron outer coordinations where electron transfer happens from the iron 2 to iron 3, and iron 3 2 becomes the iron 2, iron 3 will prefer stay at the outer state of that coordination sphere. Okay, so this is the coordination, outer coordination sphere electron transfer is being monitored by the help of the Mossbauer spectroscopy. We are able to know how this kind of electron transfer happens by taking off the iron 2. How becomes it becomes iron 3? It's taking electron, it's providing electron to the inner iron 3 system, and inner iron 3 become the iron 2. Okay, so from it we can say the Mossbauer is a very big tool, very important tool to isolate my iron complex having different amounts of different states. Oxidation state is present over if there multiple if multiple iron center is there having different oxidation state. We can easily identify by the help of the Mossbauer spectroscopy what is the amount of the my iron is present in that particular oxidation state. We can easily calculate by the population in particular state, and it will appear as a intensity. Depending on the how much intensity we have, we can easily identify the amount of my iron in that particular oxidation state. Okay, so that's all we actually covered over here. If you have some other questions, then feel free to ask me. So to summarize today's session, so can say we will discuss about first of all, so how with the different nuclei having a different I value, nuclear spin state is different, nuclear state I which is different, that is, let's suppose 3 by 2 or 5 by 2 or 7 by 2, whatever it is. So in the Mossbauer line, how if EFG not equals to 0, that means electrical field gradient is there. So how many lines we will expect to get from that Mossbauer spectroscopy? We slowly calculate that one depending on the what is the my energy gap between two state and what are the degenerate energy state with it, what are the same amount energy state we will get, a same amount energy transition we will get depending on we here the problem is the if the nucleus state has been changed from I equals to 5 by 2 to ground state is the I equals to 5 by 2 and excited state is the 7 by 2, and is that EFG equals to not equals to 0, in that case fine. Now I expect to find the number of Mossbauer line. Here I find the 6 lines, and from it we'll have a intensity ratio of that 6 lines will be 6 is to 3 is to 3 is to 2 is to 1 is to 2 is to 1. Okay, or otherwise you can say that kind of ratio you'll find for at least 6 lines you will get, and the ratio will be similar in a perspective of the which energy will come in a fire. That means we'll have a energy gap, higher energy gap will be plus minus half 2 plus minus 7, so that will come into the L at the end, that is the one ratio will be 1 only, we will get 1 ratio, and then if you think to different amount depending on it where it should come. Okay, so here is the sixth line we talked about, the 5 by 2 to plus minus, that is not the actual number 6 line. Number 6 line will be the transition between plus minus half 2 plus minus 7 by 2. This will be the at the end transition. Okay, so at the most positive direction this will be my transition. So I messed up with that numbering, so it will be depending on the how energy, if energy is required uh, more than my initial energy, that will be comes into the my at the end at the most positive direction. Okay, that's all. And from it you can calculate any nuclei, for any nuclei you can calculate how much my Mossbauer line will be present in the and depending on the I value ground state. Okay, now we discuss about the ferredoxin. So how ferredoxin um, electrons takes one electrons is giving a mixed valence C, and what are the ratio of a Mossbauer line will find, and how this antiferrotic coupling giving me a iron 2.5 virtual iron 2.5 iron 2.5 state. Okay, now we are able to detect the actual structure of the iron complex by the help of the Mossbauer spectra, depending on the ratio of the iron each particular iron atom, and then we can calculate the from the simulation, and then we can able to say that what is the actual structure of the iron 3 carbonyl complex. Okay, so and then we discuss about some research problem with the help of the some addition of the Lewis acid, that is the scandium triplet, which is actually helping to stabilize this iron 4 oxo species and giving a highly reactive iron 4 oxo species, and that can transfer oxygen to olefinic group, and the reactivity increases in presence of the scandium species, and that scandium oxo species has been isolated by the Mossbauer spectra. Depending on the delta value, it's showing that the sum of the electron density actually stabilized by this Lewis acid. Okay, and then again we also look into the iron oxo species to oxidize the olefinic group, and depending on they isolate some of the intermediates which is formed in presence of the base or absence of the base. These two are different iso intermediate has been found that has been isolated by the Mossbauer spectroscopy. Okay, so it has a strong evidence that how much population is present over here. Okay, this is a strong evidence that Mossbauer spectroscopy giving a strong result to the population density of the each particular intermediates into the systems. Okay, later on we actually discuss about some Prussian blue and the Tunis blue color, why this color happens. So depending on the different amount of isotopic level given into the reaction mixture, we are able to come into the same Mossbauer line. That means this is the one of the iron 2 actually. If in the Tunis blue, they are forming the same complex where the Prussian blue, this giving the as exact complex of the Prussian blue has been found. So because of that, this external iron 2 has been provided into the addition of the external iron 2 into the hexacyano ferric system. This iron 2 actually reduce the hexacyano ferric internal hexacyano ferric and giving me the iron 3 outer coordination site, and the inner coordination site the iron 2, which is actually found in the Prussian blue, and it is exactly same complex has been found in the Tunis blue and the Prussian blue. Okay, and then that has been actually monitored by the iso- isotopic abundant of iron 57. Okay, that's all today. So I'm going to stop over here. So in the next session, we will come into some other problems also. I'm looking to some research problems right now, and then come to know, come to show you some results for the Mossbauer spectroscopic result. And in the next session, we'll like to discuss about those problem and how to solve those problem. I want to go through some net or gate exams question paper. If I found some problems related to Mossbauer and CD spectra, I will definitely come into that problem and try to solve those problem as the next session will come. Okay, so from it I will stop over here. So if you have some doubts, please let me know in by comment in the YouTube channel, or anyhow, just give me a pin to you are finding some problem about this. Just answer those. Okay, I'll try to solve that one. Okay, to it I'll stop over here. Thank you the all for your patience going through those lecture virtually, and then try to solve in the next class. Okay, thank you all. I'll stop over here.